Hi, I'm Paul Williamson, KB5MU, and I have a few words to say about voice quality in amateur radio. Since nearly the dawn of radio in the early 20th century, the spoken voice has been one of perhaps four main kinds of program material transmitted. Written text was the first, Morse code, radio telegraph, and so on. After voice quickly came music, and after relatively few short years, video. With computers and the internet, the technical boundaries start to blur and other kinds of transmission are added. But from a consumer's point of view, these four types are still plain to see in everyday use. Amateur radio has never had much to do with music, mainly since we are prohibited from transmitting music in most circumstances. Early radio regulations were designed in part to sort stations into different types with different regulatory needs. Music transmission was, and is, strongly associated with broadcasting to the public. It's not a coincidence that broadcasting to the public is also generally prohibited on amateur radio. If not for these prohibitions, we would never have been allowed to share the amateur bands as we always have, informally, dynamically, and without much government involvement. Video has a different history. It's also strongly associated with broadcasting, but since video transmission was out of reach for amateurs in the early years, there was no need for rules prohibiting it. Even today, relatively few of us are active on amateur television. Voice is still the main thing. Amateurs have been speaking to each other over the air for 100 years, plus or minus, using a variety of different technologies, starting with simple amplitude modulation, or AM. Some of those technologies can sound pretty good, all things considered. In other cases, the quality can be downright bad, even bordering on unusable. As with anything in engineering, trade-offs are often involved. Sometimes the trade-off is against cost, which may arise from system complexity. Sometimes the trade-off is against efficient spectrum occupancy. Sometimes the trade-off is against performance in terms of the required signal-to-noise ratio for acceptable quality. And all too often, the trade-off is against the business interests of an equipment manufacturer, which may be enforced by patents or other forms of so-called intellectual property. Let's talk briefly about what makes voice sound good or bad over the air, and let's start at the very beginning. Here's one person talking to another person with no technology involved. The speaker creates sound, which is just pressure waves in the air. The listener detects these pressure waves using special hardware called ears, and processes the resulting measurements using even more special hardware called a brain. The subjective result created by that processing is what we experience as hearing. A perfect voice transmission system would be able to recreate that experience with no degradation whatsoever. Now, before we even introduce any electronics, things are not really this simple. For one thing, most listeners have two ears and the ability to turn their heads. They can experience sound within a three-dimensional space. Science doesn't yet have a complete understanding of how all that works, but we know a lot. We try to recreate this experience with stereo, binaural, quadraphonic, 5.1, DTS, DSX, Atmos, and so on. These systems are exclusively aimed at music and movie soundtrack reproduction, hardly ever for simple voice. I think this may be worth looking into someday, but for now, let's just assume that for voice purposes, we can think of the signal as being monophonic, a single channel. A system based on this assumption can never be perfectly realistic, but 100 years of radio telephony and about 135 years of wired telephony suggest that it's a good place to start. Our brains seem to be able to adapt to the missing dimensions. We have some powerful mathematics for single-channel signals. One thing we know mathematically is that any signal can be decomposed into components by frequency and reassembled without loss. So we can meaningfully describe a signal by its frequency distribution. Because of the way the human vocal tract works, a voice signal typically has a lowest frequency component, or fundamental, somewhere in the range of about 50 to 300-ish hertz. It turns out that human hearing doesn't necessarily need to actually detect the fundamental. The listener seems to hear the fundamental even if only its harmonics are present. So for voice communication systems, it's common to assume that there's no need to transmit any frequency components below 300 Hz. The voice is still considered intelligible even without its fundamental. Now, that doesn't mean the listener can't tell that those low frequencies are missing. It just means that they can still understand what's being said. Likewise, we know from measurements that human hearing is less sensitive at higher frequencies. A young person with undamaged hearing may be able to hear as high as 20 kilohertz, but this degrades with age and exposure to loud sounds to 12 kilohertz, 10 kilohertz, or even lower. Human hearing is also insensitive below about 20 hertz. So it's commonly said that the range of human hearing is 20 to 20,000 hertz. A system that reproduces all frequencies equally from 20 hertz to 20 kilohertz with perfect precision would certainly be considered a high-fidelity system, suitable for the most demanding music listening. Most listeners would be perfectly happy with a lot less and never know the difference. Experiments with voice telephony have shown that the frequencies that are most important to voice intelligibility are those from 300 hertz to just 3,000 hertz. Listeners judge a voice as intelligible even if all the components below 300 hertz or above 3,000 hertz are removed. Again, that doesn't mean the listener can't tell that the frequencies are missing. Any listener with normal hearing will certainly be able to notice the missing information. In an otherwise clean environment, a hi-fi system with wide frequency response is a superior listening experience. An interesting special case is when there are two or more voices present, all at about the same volume at the listener's ear. All the voices occupy roughly the same frequencies, so you might think that they would interfere with each other catastrophically, and the listener would be unable to make any sense out of them. But we know from common experience that this is not the case. At a crowded cocktail party surrounded by many conversations, most listeners can choose one conversation and concentrate on hearing that voice among the many, and do a pretty good job of understanding it. This is called the cocktail party effect. Everything I've just been talking about applies to voices in air. Now let's begin to introduce some electronics. Here we have a basic one-way telephone system, a microphone, a simple amplifier, and a speaker connected by wires. The microphone converts sound into electrical voltage, and the speaker converts the amplified signal back into sound. What new problems have we introduced? For one thing, the frequency response of the microphone, amplifier, and speaker won't be perfect. That is, some frequencies will be reproduced at different amplitudes than others. This is especially a problem with microphones and speakers that have been designed to be very small or very inexpensive. And it could be even worse if the mic or speaker is also designed to look cool or be waterproof or whatever. Microphones and speakers are both electromechanical systems, and so high-performance devices tend to be more difficult and more expensive. In practice, the microphone is generally designed to have limited frequency response. A microphone intended for high-fidelity music reproduction would try to cover the full range of human hearing, but a microphone intended for voice telephony might purposefully roll off around 3 kilohertz. Any response that's outside the intended range is wasted and can only cause problems. The frequency response error is not the only possible problem. The components can also be nonlinear in any number of ways, meaning that signal components can interact in ways they shouldn't, creating extra unwanted signal components. These effects are usually lumped together and called distortion. Distortion is also typically worse in cheap or miniaturized devices. The wires themselves, especially if they're long, can act as a filter and degrade the frequency response. They can pick up unwanted signals from other wires or from other nearby radio transmitters, and so on. As radio amateurs, we don't usually need to be experts at wired telephony. Instead, we add a radio transmitter and receiver to the system. We still have the imperfect microphone and speaker, and our radio transmitter has to somehow convert the audio voltage from the microphone into a signal that is suitable for transmitting over the air, and the radio receiver has to reverse that conversion. We call that modulation and demodulation. The simplest modulation is AM, amplitude modulation, where the input voltage from the microphone just varies the gain of an amplifier stage in the transmitter, so that the signal is stronger when the mic voltage is higher. This produces a radio signal that can be demodulated by a simple power detector. The simplest AM receiver and transmitter can each be implemented with just one transistor or vacuum tube. AM produces a radio signal that looks like this, viewed in the frequency domain, where amplitude is plotted against frequency. That spike in the middle, that's called the carrier. That's the signal we feed into the variable gain amplifier in the transmitter. That stuff above the carrier is ideally an exact copy of the microphone signal. It's called the upper sideband. The stuff below the carrier, the lower sideband, is another exact copy of the microphone signal, but inverted in frequency. So low voice pitches make sidebands that are close to the carrier, and higher voice pitches make sidebands that are further away. You can see this is a wasteful way to transmit a voice signal. For one thing, we're transmitting 2 copies of the voice signal, which takes extra transmitter power and uses up twice as much space on the band. Perhaps worse, a lot of our transmitter power is going into the carrier, which doesn't carry any information at all, except to provide a frequency reference. On the plus side, AM does not require any processing of the audio signal at all. The system is so simple, it just transmits a copy of the signal as it came from the microphone. That means that if our modulator and demodulator circuits are designed with care to be reasonably linear and to have nice frequency responses, the audio voltage coming out of the receiver can be a very accurate replica of the microphone signal. Of course, that only applies when radio conditions are perfect, strong signals and no interference. Nonetheless, even today, this potential for high audio quality attracts a group of amateurs who operate vintage AM radios on the 75 meter band. With care, under perfect conditions, they just sound great. Inevitably, AM came to be replaced by a less wasteful method, SSB, which stands for single sideband. It's easy to say what SSB does. It transmits just one of the 2 sidebands. It does not transmit the carrier at all. This was invented in 1915, but didn't see widespread application in amateur radio until after World War II. There are several methods to generate an SSB signal, but none of them is anything like as simple as an AM transmitter. The filter method requires a high-quality filter with flat frequency response and steep skirts, and the phase method requires a similarly high-quality 90-degree phase shifter. These complex elements tend to be imperfect, especially when designed to be low cost. You may have heard of the Collins S-line radios. They were highly prized and expensive, mainly because they used very high-quality SSB filters. With poor filters, which were more common, SSB can be pretty hard to listen to. Even with good filters, SSB has a problem. Without a carrier, there's no frequency reference, so reception depends on highly accurate and stable tuning. This is less of a problem with modern radios, which usually have good frequency accuracy and stability. But if the tuned frequency is off, the received SSB signal comes out frequency shifted by the same amount. All the voice pitches are off. When the pitches are too high, it sounds a little bit like Donald Duck. When SSB was introduced into amateur radio, many users objected. The voice quality was definitely worse. Not for any unavoidable fundamental reason. Perfectly implemented SSB can sound just as great as AM, in theory. In practice, though, SSB signals are usually not as good. Tuning them incorrectly and listening to them for long periods of time without fatigue are skills that can be difficult to learn. Nonetheless, the advantages of SSB have proven to be enough to justify the popularity of SSB over AM on the HF bands. If an interfering signal is present within the bandwidth of the desired signal, both AM and SSB pass the interference right through to the speaker. As radio conditions deteriorate and signal strength fades, the desired signal can be swallowed up by noise. However, the degradation is gradual and relatively easy to listen to. The last main analog method of modulation is FM, frequency modulation. In FM, the voltage from the microphone is used to vary the frequency of an oscillator in the transmitter instead of the gain of an amplifier, as in an AM transmitter. Like AM, an FM signal has a central carrier and 2 sidebands, but the math works out differently. It turns out that most noise and interference on the radio bands is like AM. The FM receiver naturally rejects it. However, the FM signal needs to be wider in frequency than an AM or SSB signal. An AM signal occupies a bandwidth of twice the highest audio frequency transmitted, or about 6 kilohertz for a nominal 3 kilohertz voice bandwidth. An FM signal, on the other hand, doesn't have any one particular bandwidth, but must have at least several times as much bandwidth as the audio signal in order to realize its noise reduction capabilities. A commercial broadcast FM signal, with all its auxiliary subcarriers, occupies 200 kilohertz. In amateur radio, FM signals were originally allocated 60 kilohertz channels. This has been trimmed down to 30, 25, 20, 15, and even 12.5 kilohertz in some cases because of overcrowding. Even at these reduced channel spacings, FM inherently sounds pretty good. It is still subject to degradation due to low-quality microphones and speakers, of course, and the design frequency response is still capped at around 3 kilohertz. The lowest audio frequencies are reserved for CTCSS signaling tones, so FM receivers almost always filter out everything below 300 hertz. But within these limitations, in perfect conditions, FM sounds good. As radio conditions go from perfect to merely good, the FM signal holds up well. It continues to sound good due to a phenomenon called quieting. The FM receiver suppresses background noise to a substantial extent. The standard for a good, strong FM signal is 12 dB of quieting. That is, the background noise is reduced by 12 decibels. As conditions get worse, though, the FM signal starts to fall apart. If the signal is weak, random clicks that sound a bit like popcorn popping start to intrude on the received signal. Then, as the signal gets even weaker, noise comes up and overwhelms the received signal rather quickly. Because FM occupies a much wider bandwidth, its use is not allowed below the 10-meter band. On VHF and UHF, though, FM is king, for a number of reasons. One of the big reasons is its consistently good voice quality when conditions are decent. It may be hard to believe if you tune around the bands now, but our VHF and UHF bands, especially 2 meters and 70 centimeters, used to be overcrowded. In major metropolitan areas, every available repeater pair was in use, and during prime commuting time, every repeater was busy with conversations. There was a demand for increased capacity. This was even more true in the commercial and public service radio services. Even with channel spacing split in half, and then split in half again, there were not enough channels to go around. Radio manufacturers began to develop digital technologies to try and cram more users into the available spectrum. The minimum standard for success was to fit 2 voice channels into the same 12.5 kilohertz channel that then accommodated just 1. In the 1990s and early 2000s, industry developed several competing digital radio standards, including DMR and P25. Japan Amateur Radio League developed D-Star. In 2013, Yaesu introduced their System Fusion, which is nearly identical to P25. All of these systems are now in use in amateur radio. Details vary from system to system. They all have some way of linking up systems over the internet, which seems to be the only way to find enough people to talk to anymore. We won't get into that today. Here's a very high-level view of how digital voice systems, including all of these, are put together. Instead of directly transmitting the microphone voltage, as the analog systems do, digital voice systems instead convert the microphone voltage into a sequence of numbers called samples, using an ADC, or analog to digital converter. Here's where another important mathematical theorem comes into play. The Nyquist sampling theorem says that we can always sample a signal like this. As long as the sampling rate exceeds twice the maximum bandwidth of the signal, the stream of samples captures all of the information in the signal, and the signal can be losslessly reconstructed from the samples. That may not be intuitive, even if you've studied the proof of the theorem, but it's a fact. So if we want to sample microphone data that contains frequencies up to 3,000 hertz for standard communications grade voice, we need to sample at least 6,000 times per second. The implementation turns out to be easier if we leave some extra room, so typically we will sample at 8,000 times per second. Each sample needs enough bits to accurately capture the voltage. A convenient size is 16 bits per sample. Multiply that out. 16 bits per sample times 8,000 samples per second is 128,000 bits per second. If we could somehow squeeze 128,000 bits per second through our radio channel, we could reproduce perfect voice with 3 kilohertz bandwidth. Unfortunately, it's really, really hard to get 128,000 bits per second through a radio channel without making the radio channel much wider than a standard FM voice channel. We need a way to reduce the number of bits that have to be transmitted by a lot. The algorithm that compresses the voice samples is called a voice encoder. Then on the other end, a matching algorithm that re-expands the voice samples is called a voice decoder. And together, we call the pair of algorithms a voice codec, which is short for coder-decoder. All of the digital voice standards I mentioned above use a version of the same voice codec, called AMB, which stands for Advanced Multiband Excitation. D-Star uses AMB Plus, while the others use AMB Plus 2, a more advanced version. AMB is a proprietary codec from a company called DVSI, Digital Voice Systems Incorporated. It is patented, and both the specification and all the implementation details are kept secret. Apparently, the only legal way to get your hands on an AMB voice codec for experimentation is to buy a board with a hardware chip from DVSI that contains their AMB implementation. That's what the DV dongle was, but that's no longer available. Another similar product called the Amateur Radio Thumb DV is currently showing as sold out at a discounted price of $100. Currently, the cheapest product I can find is the ZoomSpot AMB server board at $150. That gizmo will let you operate any of the digital voice modes if you have the right software to go with it, but it still won't let you modify the voice codec or even see how it works. For an experimenter service, this is not ideal. DVSI's implementation of AMB takes input samples at 8,000 samples per second, no more, and can output a compressed bit stream at rates varying from 2,000 bits per second to 9,600 bits per second. All of the digital voice modes use it at a low bit rate, around 2,400 bits per second. The voice modes then add a bunch of overhead, including some forward error correction, and transmit up to 9,600 bits per second using variations of 4-array FSK through a standard narrow radio channel. They reach the goal of transmitting 2 voice signals in the space of 1 by time division multiplexing that one channel. With these design decisions, they don't have room for any more than about 2,400 bits per second of voice data. So, how does it sound? Not that great. Under ideal conditions, with no errors on the channel, it sounds a bit like a robot in a box. Intelligibility, the ability to make out which words were said, is barely acceptable. Speaker recognition, the ability to distinguish one person's voice from another, is significantly impaired. Listener fatigue is high. It's just not in any way pleasant to listen to. When the radio signal degrades enough to introduce some errors, these digital voice modes sound worse. Distortion goes up, and intelligibility and speaker recognition go down. Even on internet connections, when radio transmission errors are not a factor, it isn't uncommon to be unable to understand what the other party is saying. When the radio signal degrades just a little more, these digital voice modes can become ridiculously bad. They can sound more like R2-D2 than like C3PO, emitting all sorts of bleeps and blorps and obnoxious noises. It can be entertaining for the first 30 seconds or so, but it's not what digital voice is supposed to sound like. I think it's a sad situation that some of the worst voice quality ever transmitted on amateur radio is being transmitted today using some of the newest transmitting equipment and some of the most complex technology. Fans of these digital modes can sometimes be heard to say that they sound great, or even better than FM. I think what they're hearing is that digital voice doesn't have the same familiar types of degradation they're used to hearing on FM. Somehow they're able to ignore the problems that are unique to ambient encoded digital voice. I am not, and I'm not alone. Amateur radio needs a better digital voice mode than these. I have good news. It's absolutely possible to make digital voice that actually sounds good. There are really only 2 steps. First, we have to give up on trying to squeeze the digital voice transmission into a legacy channel spacing that was designed for FM signals decades ago and then cut in half 3 times. A channel about 40 or 50 kilohertz wide should be plenty. We do have room for this. The amateur bands are not that crowded anymore, and it's no longer difficult to use UHF frequencies instead of 2-meter VHF. The regulations, at least in the United States, allow for much more bandwidth for digital transmissions in the 222 megahertz band and every band above that. In particular, for a digital satellite system that uses 5 gigahertz and 10 gigahertz microwave bands for the uplink and downlink respectively, as proposed by ORI, there's plenty of room for 100 of these channels. The only other thing we have to do is use a modern audio codec instead of the proprietary relic that is ambi. The codec we choose needs to be able to work at higher input sample rates. 8,000 samples per second is pretty marginal for voice quality. It must be able to work at output bit rates significantly higher than the current 2,400 bits per second in order to achieve superior compressed audio quality. Ideally, it should be able to scale up to even higher bit rates in case our standards go up and we want even more perfect voice quality. It should work well with multiple simultaneous speakers and with high levels of background sounds, including background music. It should have high-quality open source implementations. Its specifications should be open and available to all. It should be free of patent or licensing encumbrances. Does that sound too good to be true? It's not. There is an audio codec that meets all these requirements. It's called Opus. We have prototyped a digital voice mode using the Opus codec, with the goal of using it as the recommended voice mode for the P4XT digital satellite transponder being developed by ORI. We had a bit of fun with the name Opus and named this mode Opulent Voice. Here is the overview of Opus from its own website. Opus is a totally open, royalty-free, highly versatile audio codec. Opus is unmatched for interactive speech and music transmission over the internet, but is also intended for storage and streaming applications. And here is their technology summary. Check out all those awesome features. A wide range of bit rates, input sample rates, frame sizes, and audio bandwidths. It can output a constant bit rate or variable, and can handle speech or music, mono or stereo or multi-stream, all adjustable on the fly, and doesn't freak out when data is lost in transmission. Our prototype is a pair of application programs written in C++. One encodes and modulates, and the other demodulates and decodes. We use the library Opus implementation, libopus, and we tell the Opus encoder that it is encoding single-channel speech. We max out the input sample rate at 48,000 samples per second for full band frequency coverage, and choose one of their recommended frame sizes, 20 milliseconds. And importantly, we've chosen an output bit rate of 16,000 bits per second. That's between 6 and 7 times as many bits as the ambi-based digital voice modes use. 16 kilobits is actually near the low end of bit rates supported by Opus. That's appropriate since we're only encoding speech. We don't need high-fidelity reproduction of music. To simplify the prototype design, we're currently using a constant output bit rate. This will probably change to a variable bit rate in the full implementation. Credit where credit is due. We did not write our prototype from scratch. It is based on a C++ prototype written by Rob Riggs of MobileLinked LLC for the M17 Project. The M17 Project is another effort to replace the ambi-based digital voice modes with something better, but with somewhat different goals. Like us, they wanted to replace the ambi voice codec with something free and open and with better quality. But they also wanted to fit within traditional channel spacing, so they could not greatly increase the bit rate. They chose the voice codec called Codec 2, created by David Rowe of Rowatel, based on his 1997 PhD dissertation. They use it at its maximum bit rate of 3,200 bits per second, only about 1/3 faster than the ambi modes. On top of that, they use a rate 1/2 convolutional forward error correction code to protect the voice bits from errors. And we've kept that, along with many other design decisions that we didn't see any need to change. We did simplify some aspects of the M17 design and adjusted various parameters to match the requirements of our higher bitrate. Our implementation can be found at this URL. Like everything we do at ORI, it's open source, and we publish our work early and often. This prototype is a work in progress, and we invite you to participate in its further development. So, have we succeeded? It's still an early prototype, and we don't have a lot of experience using Opulent Voice in the real rough and tumble world of mobile radio, but so far the test results have been extremely promising. Voice quality through Opulent Voice is not perfect, but it is genuinely very, very good. At least I think so. What do you think? You've just listened to this entire talk through the prototype Opulent Voice implementation. As Madge would say, you're soaking in it. I'll be happy to answer any questions you may have in the remaining time. Type your questions into the chat, and I'll try to answer them.
Thank you, Paul. I'm going to turn it over to you. Yeah, please type your questions in the chat, and we'll bring you on screen.
Thank you, Jim, for your help in moderating this talk.
You're welcome. Enjoyed it.
There was a message during the talk from Dave and T9E saying audio does not match video. I assume that you meant synchronization, hopefully not some entirely different audio. I hope that cleared up for you. There's not much we can do about it here from the presentation interface. No questions coming in so far. Hopefully there's not a technical problem with that. I apologize if there is. Dave N8SBE asks, is there a way to parameterize Opus to fit in some legacy bandwidths? It's very limited. The Opus codec is not very happy with low bit rates. They can go down to about 6 kilobits, but it doesn't sound very good at that rate. I wouldn't run it below maybe 8 or 10, which would make it really hard to cram it into legacy bandwidths. It goes up really well. It goes up to 512 kilobits, I believe is the figure, somewhere in that vicinity. And at that bit rate, it's great even for high fidelity music. Okay, now the comments are suddenly coming in faster than I can read them. I hope Jim will sort them out and pick one for me. Michelle asked, what's the next step for the C++ implementation? That's a good question. There are lots of different possibilities. One thing that we're excited about trying very soon is to get it into a real handheld, preferably hardware implementation, complete with push to talk and transmit and receive live radio to radio, not through the satellite system, so that we can get some experience using it. We have a plan to use a HackRF with a PortaPack as a prototype hardware for that. Hopefully that will lead to a design that can be produced in a nice form factor. Have you considered a reference implementation in Flex Radio? If I recall correctly, they had a contributed D-Star plugin that ran radio native. Some opportunity here. That's a good idea. I believe that would be possible. I'm not familiar with all the ins and outs of the Flex Radio waveform interface, which is, I believe, what they call that. If it can handle the bandwidth and the processing load, then absolutely, that would be definitely a thing to do. Ken VA 7 KBM asks if it can work on 2 meter frequencies. The problem is bandwidth. The channel's width is and bit rate is above what at least US regulations permit on 2 meters. So no, it can't currently be used on 2 meters without some kind of a rules change. And 2 meters is the most crowded of the VHF and up bands. So maybe using it above 222 would be just as well. Elon KC1LDQ asks, are there users now experimenting with this in ham radio? Only a couple. Not as far as I know, although we published everything. So there may be people out there experimenting with it silently. But as far as I know, just me and a couple of people who work with me, mostly on the lab bench. Once we get a thing implemented into real hardware like the PortaPack, then we'll be actually trying this over the air more extensively. It's very early in the process still. Bill KF5 SPQ asks, how is this new codec implemented in hardware? In our implementations and probably every foreseeable implementation, it's in software. It's designed to run on a general purpose processor, and it does not use a huge amount of compute power. So a little ARM chip like a Raspberry Pi can do it. Michael KM5BOR, I'm sorry if I miss any of these letters, it's pretty small on my screen, asks, is this a hardware or a software product? What would you need to make Opus work? Sort of the same question. In order to actually use it, you'd need hardware. At the moment, what we've written is some software that can run on a general purpose processor with a little bit of power, and it would need interface to audio, I/O, to transmit and receive, and then some kind of radio interface. The prototype that we based it on from M17 expects to talk to a device that transmits and receives FM. So that would have to be converted into an IQ sample stream to use it with a straight SDR. But an SDR would be the obvious thing to use this with. But it could be used with just a little bit of processing power and an FM radio that had enough bandwidth. Donald KA4NDY says, great info. Excited you're working toward quality sounding digital communications. I resisted purchasing digital equipment until all settled down a bit, but did buy a DMR HT. So what time frame do you estimate new radios using this technology? That's a good question, without a good answer yet. To actually be able to go down to the radio store and buy one, in a nice little package, that may be quite a while, because convincing manufacturers that it's in their interest to build something new, it's kind of a chicken and egg problem. They don't want to build it until there's lots of users, and there can't be lots of users until after they've built it. We're thinking about different ways to jumpstart that, maybe produce something that's a little less mass produced and probably a little more expensive as a result, to make it available for people to mess with. And it'll be part of the ground station for the satellite system, if and when we're able to get that put together. These are long-term projects. So I'm not asking you to start saving your money to go buy one just yet. It's not a product yet. We hope it will be. Dennis K for DGW asks, what is the minimum SNR for good digital voice? And that is an excellent question too, which we have not yet made an attempt to measure. It's not going to be very much worse. It's going to be a little bit worse than one of the existing digital voice modes, simply because the bandwidth is higher. And I wish I had a better answer for that. We have not done the analysis or the experiments to give a definitive number yet. John KD3H says, do you have thoughts on stimulating adoption of Opus in commercial radios, HT mobile HF base stations? Have you looked at what Opus might look like in silicon, as it were? We have thought about it some. We're not going to be able to get into HF base stations. This is just not the bandwidth available. HTs and mobiles, possibly. In silicon, it'll be interesting. We have been treating Opus as primarily a black box for the time being, since it meets our needs so excellently. So I don't even know what's in there in any great detail. So it's hard for me to visualize whether it would be feasible to make it better or cheaper by implementing it in hardware in silicon. Maybe. My guess is, based on general experience in the industry, that probably the right way to put this into silicon is to put a processor into silicon and write some software. I think that's what it was designed for. But it may be the case that an ASIC or an FPGA could do a better job with some work. As far as stimulating adoption, I think no, we don't have any great ideas. Trying to get it into some kind of implementation in people's hands is the first step, I believe. Once people get excited about it, then manufacturers can be approached. James B9 ACQ says, I currently use some Yaesu radios that can run Fusion, C4 FM. Am I correct that they also use the MB codec? Yes, that is one of the digital modes that uses the MB codec at low bit rates. Donald K4NDY, maybe this can be implemented via app on Android controlled radio like the RFinder. If the radio has sufficient bandwidth and the Android phone, which has sufficient processing horsepower, which it probably does, then yes, that would be possible. You'd need access to the programming environment and permissions to access audio and the radio at that low level. It's a small matter of programming, as they say. Did I catch up? I think I caught up. More questions and comments are welcome. We have some minutes left to go. Douglas AB7DG wants to know, what's your best estimate on when this technology will become available for non-technical amateurs? It would be a guess. I can give you a lower bound. It won't be available for to go buy and just use for at least a year. It might be several if things go slowly. You don't have to be very technical to use the software implementation, though. If it gets wrapped up into a nice package, there's no reason why it would have to be inaccessible to any amateur user. Could it be any worse to use than something like FT8, which is threatened to take over the world? So I don't know. While waiting for more questions to come in, I can give a little speech about open source. ORI tries to do all its work completely in public. We develop stuff with the aid of anybody who will help, including you, all of you guys out there. Come join us and help us do this work. But we publish as soon as there's anything comprehensible to publish. That means that sometimes we're at Ham Expo giving a talk about stuff we've just done, and it's not fully fleshed out yet, or we don't have a complete plan to the future. So some of my vague answers are because of that. We're open process, and that means sometimes stuff comes out into public a little bit half-baked. ORI, Open Research Institute, has a Kumo space room available from the conference interface. And several of us who have been working on this will be available from time to time in that room. So feel free to drop by. If in the unlikely event that this Q&A session runs long, we can switch it over to there. So everybody's welcome. There's a new question. Mark G4 HGL says, what do you consider developing an open source lower bitrate codec for use on the lower frequency bands? In principle, yes, but in practice, I'm not a voice codec designer. I'm reliant on the voice codec designers who are already out there. At the lower bit rates, extremely low bit rates that might be usable on HF, Mike Rowe and his work with Codec 2 are way ahead. They even have products you can buy that would interface your radio to a microphone and speaker and use their digital voice mode. In order to outperform that, we'd need codec development in the low bit rate range. And my interest is in higher voice quality and not in occupying every frequency band on amateur radio. So it's probably not something I would work on personally, but there's no reason why it wouldn't be a worthy project for somebody who is interested in doing that. Michelle asked, how can people join up and help make things happen? Well, go to our website, openresearch.institute, and there's a link near the top that says Getting Started, and it has all the different places you can join. There's a Slack group for chat, day-to-day operational work. There's a GitHub where all our source is archived, including the source for the prototype C++ implementation of Opulent Voice, documents as we develop them, and so on. So we're open to anybody who wants to work. You don't have to be an expert. You might accidentally become an expert. Seeing new questions. Have I answered every question in the world? Probably not.
So now would be a time if you've got any questions to go ahead and bring them in. Otherwise, we can just take this to Kumo Space and people can actually chat voice to voice if people want to go over there now. So nothing seen over on the question side. So what do you say, Paul? Should we go ahead and close her down?
I guess so. Thank you all for your attention, and thank you, Jim, for helping with the presentation.
Yeah. Thank you, everybody, for joining us. Very, very interesting topic. I've been a fan of the voice modes digital voice modes, because they allowed me to talk around the world with an HT my first year that I became a ham. So I've enjoyed that a lot. Still participate in them, and looking forward to, I think higher bandwidth is one of the biggest clues this whole thing. Here at home, I don't have a repeater nearby, so I have to deal with hotspots. And once I started getting, I had fiber, and I had 50 up and 50 down.
Yeah.
My RTD2 just seemed to trickle away.
Yes.
Yeah, and I think the same is true for a lot of folks. But no, this is very, very interesting. Hopefully, we'll get a manufacturer on board that wants to join with you and make some things happen. So Thank you, Paul. And I see no more questions coming in, so we will go ahead and end the stream. And thank you very much all for attending.
Enjoy the rest of Ham Expo.
Yep, enjoy the rest of it. There's a lot more out there to see. There's multiple things going on, and they will be online for days to come for everyone that registered. So thank you much, and I'll just say 7-3.
7-3.